So, on to fatty acid synthesis. So, as a couple of ways to sort of compare and contrast, when we talked about beta oxidation, which is fatty acid breakdown, we had oxidation, hydration, and cleavage, and we looked at these changes in functional groups. And we also had this slide in this video where we sort of talked about that same oxidation, cleavage that happened again in the mitochondria with fatty acids. And now we're going to be looking at the reverse of this happening in the cytosol. And we're going to see condensation, reduction, dehydration, reduction. So just as a way to sort of compare and contrast, our first slide here is going to sort of walk through those chemistries. I will highlight, like with beta oxidation, for the most part, you do not need to know the enzyme names. I'll highlight ones that you do need to know. But this process happens in the cytosol with a multi-enzyme complex called fatty acid synthase. So in this video, we're going to sort of learn about the chemistry for the condensation, reduction, dehydration, reduction sort of steps. And then we're going to have a separate video that actually looks at the chemistry for what happens in fatty acid synthase. And I want you to be able to think about how this multi-enzyme complex works, much like when we learned about pyruvate dehydrogenase and we had that long arm that could sort of dip into different domains. We're going to see the same thing with fatty acid synthase. So first video here is going to be on the shorter side. We're just going to walk through those steps of condensation reduction, dehydration reduction. So zooming in here every once in a while to kind of highlight. So the condensation step here is going to occur between acetyl-CoA, that's a 2-carbon piece. Malonyl-CoA in net is a 2-carbon piece, because what's going to happen is we are going to decarboxylate that, create this carbon atom as a nucleophile, and then that is going to be able to be coupled together to create a 4-carbon piece. So that's kind of, this is the condensation step that we sort of have here. And so to label a few pieces here with this condensation step, we're going to have our acetyl-CoA here be an electrophile. Our malonyl-CoA is going to be our nucleophile. Okay, and we're going to look at the details of this on fatty acid synthase in another video, so don't worry about the details here, but I want to highlight them. The first thing that's going to happen is each of these is sort of loaded on the acyl carrier protein. Okay, so we're going to call this step loading. Okay, and we're going to see these details when we go through fatty acid synthase. So once we load these together, what's going to happen is chemistry is going to happen. So I'm going to highlight here this condensation chemistry, okay? This condensation chemistry that we're going to see, this is what happens right here. This is an enzyme. I sort of want you to know acyl carrier protein, and I want you to know this KS domain, okay? You don't need to remember the full name. You can just remember this is KS. So KS, you can remember, has to do with, and I'm spelling this chemistry with a K, chemistry, okay? You can sort of remember that that's where the chemistry step happens. But that's where our nucleophile and electrophile come together. We are going to be joining these 2-carbon pieces together to generate our 4-carbon growing fatty acid. Okay, so when we think about this chemistry happening, and this is how we're going to set up chemistry with fatty acid synthase, it is a multi-enzyme complex that really has 2 general domains. We've got one domain that's responsible for doing this condensation chemistry, okay, and then we're going to have the other sort of section that's responsible for doing the rest of this reduction, dehydration, reduction step. So let's take a moment and sort of just review what those reduction, dehydration, reduction steps are. So after we sort of do this coupling chemistry, here's 2 carbons that are going to have this functional group. We're going to have a ketone. We're going to need to do a reduction step, okay? So highlighting where we're going to see these. This is our first reduction step, okay? When you reduce a ketone, you are going to get, in this case, an alcohol. Okay, then we're going to do a dehydration step. So we're going to lose water, and we're going to get an alkene. Right, so this is our dehydration step here. And then we're going to do a final reduction step. Okay, and that's going to get us to our alkane. And I hope you see the parallels here with what we saw with beta fatty acid metabolism, where we're breaking down in beta oxidation. Okay, so our last reduction step. I'm going to color code these, and again, we'll find where they are structurally over on the right. So again, this step where we're doing this first reduction step, after we finish doing sort of our coupling here, and we've got this portion of the molecule here that has our ketone. Okay, so again, we're going to have this guy that is going to be reduced to an alcohol. So kind of this, and you do not need to know these steps or these enzyme names. I do want you to know the steps and sort of the step names and the functional groups that are changing. So that is where we're generating, again, taking our ketone there and generating an alcohol. Okay. Next step is where we're going to have our dehydration. So pick a color here. We're going to have our dehydration step. So dehydration step that we have there. So coming over here we can see that we've got our alcohol here, going to be dehydrated to generate our alkene. So here is where this chemistry is happening. Okay, so here's that guy. Okay. Next step is we are going to take that alkene, do a further reduction step, generate our alkane. So here again, we're going to do another reduction step with that alkene. So here we can see this here. Okay, here we're going to have our alkene. Again, do not need to know any of the names of these enzymes here. Okay, but it's a reductase enzyme. That kind of makes sense. We're going to take that alkene and make it into an alkane. So that's sort of our final piece here. Labeling that guy. So we've got our final functional group here as an alkane. Okay. And that was this guy up here. So I'll zoom out here so we can sort of see this all at once and not sort of be zooming back and forth. But this is, again, the chemistry that happens with fatty acid synthase. Okay, we are going to have loading of our electrophile and nucleophile onto our acyl carrier proteins. Chemistry happens in that KS domain. That's what happens sort of in, let's say, the basement level of fatty acid synthase. And then we're going to move on up to the upper levels where we're going to be able to do these functional group transformations. Reduction, dehydration, reduction. And then we're going to repeat. Okay? So every time adding 2 carbon atoms, so we're going to go 2, 4, 6, 8, all the way up to C18 or C16. So when is this process done? This process is done when you have a C16 fatty acid, okay, that is going to be saturated, okay, and then it's going to be attached onto our acyl carrier protein. Okay, so what needs to sort of happen next? Let me zoom in here. This says after 7 cycles, so 7 cycles is going to generate that C16 fatty acid. Now we're going to have that C16 fatty acid that's attached onto that acyl carrier protein. That's that long arm that's been dipping back and forth. So what's going to happen is you're going to have some esterase activity that's going to break this thioester bond and liberate your free C16 fatty acid. Okay, so I'm going to kind of highlight here that this is sort of our last step that we have here. Once we're done, we are going to eliminate and we are going to get a C16 fatty acid. Fatty acid. You'll see why I'm writing P there in a second, which is palmitic acid. Now, here's some other things that can happen, and there's like tons of enzymes and really fascinating biochemistry that are involved with this, but this is all that I need you to know. If you need to make something longer than C16, so C18 plus, you're going to use enzymes called elongases. Okay, if you need to add in some units of unsaturation, okay, you need to make it unsaturated fatty acid, you are going to use desaturases. Remembering a few important key pieces, these units of unsaturation are never going to be before carbon 9, never before C9, okay? And we are not going to make omega-3 or omega-6 fatty acids. We're never going to have a double bond that's 3 units or 6 units from the end of our fatty acid, because those are the essential fatty acids. Essential meaning we cannot make them, we need to consume them in our diet. So sort of wrapping up this little piece here and highlighting, okay, so now we've got these fatty acids, what do we need to do with them? And so basically we're going to take dihydroxyacetone phosphate, we're going to siphon that off of glycolysis. We're going to do some reduction chemistry. Okay, that's going to generate glycerol 3-phosphate. Okay, generating glycerol 3-phosphate, couple of pathways. We can add 2 fatty acids, and that's going to give us our phospholipids. So making things like lipid bilayers, things like that, that's going to be by taking that glycerol 3-phosphate, adding 2 phospholipids. Or I'm sorry, 2 fatty acids. When we add 3 fatty acids, that's how we're going to get to our triglycerides. And again, these can be exported for storage in adipose. Okay? So sort of zooming out there, that is the basic biochemistry that we're going to see from fatty acid synthase. That condensation, reduction, dehydration, reduction, we're going to repeat that until we get something that is 16 carbon atoms long as a fatty acid. Then we're going to release it from our fatty acid synthase, and then if we need elongases or desaturases to make it longer, add units of unsaturation, we'll do that. And then to use these fatty acids, we can append them onto a glycerol backbone to make either phospholipids for lipid bilayers, or we can store them by putting 3 of them on a glycerol backbone, making our triglyceride and storing it in adipose tissue.